Okay, we're recording. Okay, welcome again to chapter 12 of our GOB course. This is Organic Chemistry of Alkanes. So we've shifted now from inorganic chemistry and we're moving into the organic chemistry part of GOB. Okay, so the topics, we should probably talk about the topics. So we're going to introduce generally what organic chemistry is. We are going to look at the structures and names of alkanes. We'll look at branched chain alkanes, the condensed and skeletal structures. Some people call them line angle. I prefer skeletal, but just in case you see line angle mentioned somewhere. We'll look at IUPAC nomenclature, physical properties of alkanes, chemical properties of alkanes, and then finally cycloalkanes. Okay, so organic chemistry, historically, organic chemistry came from studying organic life or organisms. So early natural philosophers noticed that the goopy stuff that you and I are made of seems different than the hard stuff that a rock is made of. So it was clustered into living chemistry or organic chemistry, the chemistry of organisms, and inorganic chemistry, which just means not living, not the chemistry of organisms. That's the historical separation of where it came from. Nowadays, in addition to that, we say that an organic chemist studies carbon-based compounds in general, but an organic molecule must contain at least one carbon-carbon bond and/or a carbon-hydrogen bond. So, for example, carbon dioxide contains carbon, but it's not organic because there's no carbon-hydrogen bonds, there's no carbon-carbon bonds. So again, just having carbon is not enough. You need to then bond like an organic compound. So carbon dioxide is inorganic. On the other hand, methane, CH4, which is the gas that you have in your home that you use to heat your home or on your gas range, that would be organic because it contains carbon-hydrogen bonds. Okay, so there's that. Okay. So having got the definitions out the way, let's have a look at alkanes. So an alkane is just another name for an alkane is a hydrocarbon. Hydrocarbon, like the name suggests, contains only carbon and hydrogen. And it's a good starting point as we look at organic chemistry that you learn the first 10 alkanes. So let's look at the first 10 alkanes, which actually are on this slide. I've skipped the slide, but I'll go back to it. These are the first 10 straight chain alkanes. So methane contains one carbon, ethane or ethane, 2 carbons, propane is 3, butane is 4 carbons, pentane is 5, hexane is 6, heptane, octane, nonane, and finally decane is 10. And as you can see, they're just long chains of hydrocarbons. They all obey the formula CnH2n+2. For example, if N is 1, then 2 ones are 2 plus 2 is 4. So we get this formula CH4. If we look at hexane, N is 6. So 2 6s are 12 plus 2 is 14. We get the formula C6H14. So again, you can predict the formula because it obeys the structure even beyond 10 carbons. And this is definitely one thing to look out for. You know, if you want to call yourself an alkane, you have to obey this formula. So this is the slide I skipped, so I've gone back to it now. We can see here methane. Now this is not the structure of methane. This is how you draw it on a piece of paper or in a textbook. we just write a carbon with 4 hydrogens on the outside. This thing here, the more complicated tetrahedral structure, this is really what it looks like. So we have bond angles, and it's drawn in 3 dimensions. Again, you'll see both drawn in different contexts in any textbook. Whenever we draw something that looks like it has 90-degree bond angles, it's just to get it on a page. It's a cartoon. They call it a Lewis structure. But if we write the real shape, the real molecular structure, it looks more like this with a 109.5 degree bond angle. Okay, it is highly recommended, even in this course where it's open notes, that you would commit this table to memory, because in any open note exam, you're not going to have time to triple check everything in your notes. So we definitely need to know some stuff in addition to just having access to it. Okay. Okay, so the alkanes. Oh, I guess one of the things, seen as the structure right there, it would be a shame to miss. We noticed that in alkanes, all the carbons form 4 bonds, 4 single bonds, and all the hydrogens form 1 bond. So we definitely want to point that out. Also, thinking back to when we talked about bonds a few chapters ago, we can see that all the hydrogens and carbons in alkanes are isoelectronic with a noble gas. So hydrogen has 2 electrons available to it, so it's isoelectronic with helium. Carbon has 8 electrons available to it, it's isoelectronic with neon. Okay, skeletal. I think this is the first time we're ever going to see skeletal structures, which is great, because once we see skeletal, we'll never, we will go back, but real organic chemists only draw skeletal. Okay, so a skeletal structure, every carbon is a dot, and a line between dots is a bond. So for example, here we have hexane, C6H14. It's a series of 6 dots with 5 lines connecting them. I have to count them. It's got 6 dots with 5 lines connecting them. We don't deliberately draw the hydrogens on a skeletal structure. It's just implied that they're there. So for example, I know that this dot on the end must be a CH3, because I know carbon needs to be surrounded by 8 electrons, and I've only drawn 1 bond, which represents 2 electrons. So I infer there must be 3 other things attached to it. What could that be? It's hydrogen. If we look at the second dot here at the apex, that has 2 bonds associated with it. So there must be 2 other bonds to make 4 bonds total. So I infer there's 2 hydrogens. We can see here, we can have a branching point. So this is a branched alkane, where instead of just being a straight line, we have this branching point here. Again, the carbon, it looks like I guess a Mercedes-Benz symbol. Trade there. It looks like a Mercedes-Benz symbol in the middle here. If you look at the point right in the middle, we can see it's got a bond going up and then 2 bonds coming out. So that carbon in the middle has 3 bonds clearly displayed. So there must be a 4th bond. That 4th bond must be a hydrogen. Here we can see a quaternary branching point. We've got 4 bonds coming out of that point. So we can infer that there are no other hydrogens associated with that carbon. So if we look at these structures here, we have a linear skeletal structure. So it literally looks like the skeleton of the backbone or the skeleton of an alkene. We have a linear hexane, and then we have 2 branched versions, but they all have the same molecular formula as hexane, namely C6H14. So I like to call these Mr. Potato Head. because you've literally broken something and then stuck it on somewhere else, just like with one of those Mr. Potato Head toys. So it's okay to think that, but you don't want to say that. So the proper name is constitutional isomer. The constituents have been altered. In this case, they've been branched in different ways. So they are related to each other. They're all the same structure. That's what the iso of isomer means. They have the same structure. Sorry, they have the same formula, but they have different structures. That's how they differ. Okay. So here we have a nice honeycomb. Let's talk about the honeycomb first. The honeycomb is what we imagine is there on the page when we draw our skeletal structures. So if you wondered why the hexane was this nice zigzaggy structure, if you were to superimpose that zigzag on the honeycomb, you can see it would superimpose nicely anywhere on this honeycomb. So the honeycomb, you know, like math paper typically is that square paper where everything's a square. Well, this is organic skeletal paper. It's a honeycomb. And as much as you can, you want to stick to a honeycomb scaffolding for your structures. So for example, if I went from the full or complete structural formula of propane, which is C3H8, I could write it as a skeletal structure just by having this apex motif, which would fit nicely on the honeycomb. I could go up, down. I could go down, up. I could do anything as long as it's superimposed on a honeycomb. And again, this is just a convention. An intermediary between the complete structure on the left and the skeletal structure on the right is something called a condensed structure. And as you can see, we've kind of not got as much information as on the left. We've got more than on the right. It's kind of in the middle. And to interpret that, here it's color-coded black, red, and blue. So read them from the left to right. The black carbon has 3 hydrogens, so it's a CH3 group. So we just write CH3. Then in the middle, the red color, we have C with 2 H's, so that's just CH2. And then finally on the right, we have the blue carbon, which is a C with 3 H's again, so we just write CH3. It's important in our class that we can, given any one of these, we could produce the other 2. And certainly in any assessment, you might be given one and asked to produce the others. Or you might be given one and out of necessity, you have to produce another one to do another part of the problem. So full or complete structures expose everything. Condensed structures condense everything except the actual elements. Skeletal structures represent carbons as dots and bonds between carbons as lines. And that's all for drawing the skeletal structure of alkanes. When we look at the skeletal structures of other organic compounds in another video, then we'll talk about exceptions to this. But for this video, that's all we're going to need. Naming alkanes. Okay, so there are many ways you can name chemicals, but in the mid-90s, I think 1998-ish, it was unified to try and bring all these different factions of naming conventions into one common naming convention. And this was done in Europe, and it's known as the IUPAC Convention, where IUPAC is an acronym that I believe stands for International Union of Pure and Applied Chemists. And this is the modern naming convention that we adopt for all chemicals, including alkanes. So the first thing we need to do is look at groups. So we've already said that alkanes, we've identified the list of carbon 1 through carbon 10, and we said that you are advised to memorize those. So methane, ethane, propane, etc. we also, when we need to name them, we're going to have branches off of the main chain. And we need to name those branches as well. And we name them as what's called alkyl groups. So over here on the left, we have alkyl groups. They're going to be the branches on the trunk of the name. So I'm going to talk about the trunk, which is the regular, the longest continuous chain of carbon atoms. And then off of that, we can sprout branches. They're going to be the alkyl groups. To generate the alkyl group name, again, you want to know the name of 1 through 10 carbons. And it's going to be the same as the alkane name, but we take the prefix without the suffix ane, and we add a new suffix -ol. So methane becomes methyl, ethane becomes ethyl, propane becomes propyl, butane becomes butyl, etc., all the way through decyl, the decane. Okay, so here we've got a couple of compounds, or 3 compounds with the names, and we'll talk about how you get them. So the first thing you do is you identify the longest continuous chain of carbons. That's not always going to be horizontal. It might be all squiggly like a piece of spaghetti, but you're going to have to count carbons a few times and see, okay, what's the longest continuous chain? So if you look at this first compound on the left, we can see the longest continuous chain happens to be the one that's written horizontally. But again, that won't always be the case. So if I can be as creative to, why do you do that? Why not red? Okay. All right, so we can see the longest continuous chain here is this chain. So this is our trunk, like the trunk of a tree. And if you count how many carbons are in this trunk, there are 5. So the trunk is pentane. So we're going to read them left to right, but we're going to construct them right to left. So I've got a pentane trunk of my tree, and then I've got branches. Well, first of all, I'm going to number the trunk. So you want to, well, actually, let's steady our horses. I'm going to identify the groups, the alkyl groups or the branches. Okay, so they're in blue. Notice they are methyl groups. And I've got 2 of them, so that's why it's dimethyl. So it's dimethyl, but they're still methyl groups. Then you identify the location. Now there's a convention, you want the numerical location to have the lowest numbers possible. So I could either number my trunk left to right, or I could number it right to left. If I number it left to right, I would number these branches on carbon 2 and carbon 3 of 5. If I number it right to left, I would number it on carbon 3 and carbon 4. Right? I have a stylus here. I don't know why I'm struggling to write. I'm just not sure. Oh, here we go. My stylus works. All right. Sorry about that. Let's use the stylus. So again, if I number these, I can number them left to right. So 1, carbon 2, carbon 3, carbon 4, carbon 5. Or I can number it carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. But the convention says you want the numbers to be lowest as possible. So 2 and 3 is lower than 3 and 4. So that's why I opt for 2 and 3. So now I've constructed it. Let's read it left to right. I've got 2,3-dimethyl pentane, which means I have 2 methyl groups on carbons 2 and 3 of a pentane factor. So the name allows you to construct the molecule. The molecule allows you to construct the name. Okay, I'm going to clear those drawings. The second molecule, it's a bit of a mismatch of a skeletal structure with other bits and pieces. clearly, if we look, we've identified our longest continuous carbon chain, which is that one. So it's got 1, 2, 3, 4, 5, 6, 7, 8 carbons. So octane is our longest continuous chain of carbon. Then I've got my branch points. That's a branch. And then this is a branch. So I've got a methyl branch because it's got 1 carbon, and I've got an ethyl branch because it's got 2 carbons. So now, because they're different, the convention is reading from left to right, you alphabetize them. So E for ethyl is read first, so it's on the left of M for methyl, because E comes before M in the alphabet. Again, I want to prioritize the lowest numbers possible. So clearly the closest to the right side. So I would number it right to left. So that would be the first carbon, second carbon, third, fourth, fifth, sixth, seventh, eighth of the carbon backbone. So I've got a methyl group on carbon 3, so 3 methyl. I've got an ethyl group on carbon 4, 4 ethyl, and I say ethyl before methyl because it's alphabetized. So putting it all together, 4 ethyl, 3 methyl octane. Notice you separate numbers if they're clustered by a comma. You separate numbers and words by a hyphen. And there's no gap in the name. Other than commas and hyphens used appropriately, there's no space in the names. In this final example here, we can identify the longest continuous carbon chain, which is this guy by the looks of it. Again, it's not always going to be the horizontal one. It could be, you could have something that's all wiggly like that with branch points off of it. So you would have to interrogate the molecule looking for the longest chain. And incidentally, I've just posted a video on alkane nomenclature, so just to alert my students to that at least. Although usually it's actually not my students that watch my videos, it's usually students in other countries, but there you go. I at least make them for my students. Okay, so we have 8 carbons, so that's where it's gone black again. There we go. I don't know why, because it says red here, but it's having none of it. Let's see why that's black. No, erase. Right, erase. No, don't even erase. Will it draw? And having a malfunction. Yes, now it's drawing. All right, now it's working. Okay, so we have octane because we have 8 carbons. We can see if I count right to left, I hit my first branch after carbon 3, which is closer than if I count left to right. So that's carbon 1, 2, 3, 4, 5, 6, 7, 8. All right, let's change the color. It looks like I have an ethyl and an ethyl. I've got 2 ethyls on carbon 3. So that's 3,3-diethyl. Even though I've called it diethyl because there's 2 of them, when you alphabetize it, you look at the group, not the quantity of groups. So this would alphabetize as an E, not as a D. So it's alphabetized as an E, not as D. So they're both, 2 of them are both on carbon 3. That's why we put the number 3 twice. Then I've got this funny thing here. It's an isopropyl group. So it's propyl, but instead of being in a long chain of 3 carbons, it's branched in the middle point. So it's an isopropyl group rather than a propyl group. It's alphabetized as I, so it's read after the E. But again, when we construct it from right to left, we would write it before the E. And then It's same as a methyl. I don't see a methyl. Oh, here it is. Sorry. It's really, it's the way I've drawn it. There's the methyl here on carbon 4. So again, if they've highlighted in red the E, the I, and the M, they are alphabetized when read from left to right. So again, I've got a methyl group on carbon 4, so 4-methyl. I've got an isopropyl group on carbon 5, 5-isopropyl. And I've got 2 ethyl groups on carbon 3, 3,3-diethyl. You don't always have the lowest number first. So here it's a coincidence that the numbers 3 are before 5, but then we go down to 4. The number just locates the groups. If the groups are alphabetized, that's why we prioritize the groups, not the numbers. So 3,3-diethyl, 5-isopropyl, 4-methyl octane. So it's a long name. It looks complicated, but it's very logically constructed. Okay, and again, for my students that look at my other videos, I've just posted a alkane nomenclature video. Okay, so that's some nomenclature, physical and chemical properties. So physical properties first. So if we look at 1, 2, 3, 4, 5, 6, 8, 10. So this is a 8, an almost complete representation of all 10 of them. It's skipped 7 and 9 out for random reasons. But anyway, as you can see, as the number of carbons and hydrogens increases going down this group, the physical properties increase. So what's happening here is that, let's see what color am I in. So number of electrons, it's actually the electrons that's doing it, are proportional to something called London dispersion forces. So London dispersion forces are the only intermolecular force present in alkanes. So intermolecular forces are what bind adjacent molecules together. And the more they bind, the stronger the intermolecular forces. Well, alkanes only have one type, and it happens to be the weakest type, London dispersion forces. London dispersion forces are dictated by how many electrons you have. So as we go down this group, you can see that the number of atoms increase, and those atoms have more and more electrons. So we're really looking at increasing electrons going down that group. And as you can see, the boiling and the melting point increase. You can also see that as the physical properties increase, we shift from a solid to a liquid, and ultimately we would hit, from a gas to a liquid, and then ultimately we would hit a solid if the list continued. And that's because the more intermolecular forces you have, the more they bind adjacent molecules together, and eventually, if you get big enough, you become a solid. So we can see that trend in alkanes. So that's the physical properties. Chemical properties. The chemistry of alkanes, it's kind of bland. You don't have a lot of exotic structure to play with. We typically, industrially, humans use alkanes as fuels. So octane or gasoline we use as a fuel. They tend to have low value, although gas can be expensive, especially recently. It's pennies on the dollar compared to, for example, pharmaceutical, which is a much higher value chemical. So anything whose purpose is to set fire to generate energy, that's a low value product. So alkanes are typically a low value product. We burn them at home. So this first equation here, methane gas plus oxygen gives carbon dioxide and water. That's the blue gas in your gas range at home or in your boiler. your hot water boiler at home. Again, we just set fire to it. It's a low value product. That's if we have complete combustion. If we have incomplete combustion, we can generate carbon soot. So this carbon solid would be black deposits of carbon. You typically get that if you have a yellow flame, any yellow flecks in your blue flame. If you see that at home, get the gas company out, because that's also going to generate carbon monoxide, which is toxic. But anyway, so combustion is just the academic word for burn. So we set fire to alkanes to generate heat. We can also do some redox chemistry. So instead of just generating combustion products, which are CO2, so combustion just means take your fuel, add oxygen to every element in the fuel. So carbon plus oxygen gives CO2. Hydrogen plus oxygen gives H2O. We can oxidize the same fuel, but instead of just adding oxygen, we oxidize, which means we essentially insert elemental oxygen. So you can see here, I've inserted elemental oxygen into methane to generate methanol. So I've essentially got an oxygen stuck in the fuel. So methanol is a higher value product than methane. Yes, you can burn it to generate energy, but it's got too high a value. You can burn diamond to generate energy. You're not going to do that either. So we don't burn things with high value, even if they're burnable. We can make things like aldehydes. They're very high value. We're not going to burn those as fuels. And if we take something like ethane, so the C2H6 compound here, we can generate ethanol. Definitely not going to burn that. I'm saying you're not going to burn it. We actually do in the flex fuel. So the E85 fuel can actually come with up to 15% ethanol. But for the most part, you can license this and make people dance at weddings. So this would be recreational alcohol. Or it's used as a feedstock in many other industrial processes. So the bottom line here is you can burn it, you can add oxygen to it, but you're very limited to what you can do with alkanes because they're a low value. They don't have a lot of features to play with. Cycloalkanes to finish off. So this is the last slide I have for this video. So cycloalkanes are just ring structures where the alkane bends in on itself. You can have 3-membered rings, you can have 5-membered rings, 6-membered rings, however many rings you want. And we can name those as well. By definition, so the priority with acyclic alkanes or linear alkanes was to identify the longest continuous chain of carbons, and then assign the lowest possible number to any branch points. By definition, a ring, it starts with the branch point. So for example, here we have cyclopropane with a methyl group. And rather than say 1, because that's the lowest number I can give the methyl group, we just define it in position 1. So we don't need to put 1 because it's implied it has to be in position 1. So we just call it methyl cyclopropane. Again, it's not 1 methyl cyclopropane, the 1 is assumed. If we have cyclopentane here, 5-membered ring with 2 methyls, we want to assign those to positions 1 and 2 by definition. One of them is in position 1. And then I can either go round one way to give it position 5, or I can just go the other way and give it position 2. So 1 and 2 is preferred over 1 and 5. So it's 1,2-dimethyl cyclopentane. If you have 2 methyls on the same group, it would be 1,1-dimethyl cyclohexane, as in this example. Again, we're going to alphabetize groups. So if we have an ethyl group and a methyl group, the ethyl comes first. And you can assign priority to the ethyl group because you hit it alphabetically. And then if we have something like this, a dimethyl group and an ethyl group, again, we're going to prioritize them dimethyl because there's two of them. So our options, if we called ethyl 1, it would be 1, 4, 4. So rather than 1, 4, 4, we prefer 4, 1, 1 because 1, 4, 4, we have more 4s than if we had 4, 1, 1. We have more 1s now, so we prioritize that. So we have 4 ethyl 1, 1 dimethyl cyclohexane. In this structure here, it's a cycloheptane. It's a 7-membered ring. We've got an ethyl and a methyl. Again, we alphabetize the E before the M. They're both on the same carbon. 1 ethyl, 1 methyl cycloheptane. And here, our dominant, we have 2 rings, but our dominant ring, our longest chain, if you like, is a cyclohexane, 6-membered ring. And then branching off of that, we have a methyl and a cyclopropyl, both on carbon 1. So we would alphabetize the C for cyclopropyl ahead of the M for methyl. So 1 cyclopropyl, 1 methyl cyclohexane. Okay, and that will conclude the video. So I'm going to hit stop record.